Okay, 9.3, we're going to talk about the two-prop z-test today. So if you have a test for a difference in proportions, so you have a choice here really. So you can, you can say this actually either way. So the null is always the same. It's either the first proportion minus the second proportion is 0. There's no difference between the two. There's nothing going on. There's no difference. Or you set the two of them equal to each other. And different students have different preferences there. It doesn't really matter to me. So you can actually say the null either way. But for a two-prop test, it's pretty much the same null every time. It's one of those guys. So the null is nothing's unusual, that the first hypothesized value is the same, first proportion is the same as the second proportion there. So either way you want to say it, say they're equal, or you subtract them, you get 0. Whichever way kind of you're happy with. Okay, so significant test here. So by the way, if you are in class, you're going to get this sheet. It's a two-prop z-test sheet that kind of lays out all the steps there on one piece of paper. So if you want to look at that, that does give the steps for this problem, which might be nice for you to have. Okay. Research designed a study to compare the proportion of children who come to school without eating breakfast in 2 low-income elementary schools. A simple random sample of 80 students found that 1 in 19 missed breakfast today. School 2, 26 out of 150 missed breakfast today. More than 1,500 students, I'm saying it's a large school. Do these data give convincing evidence of a difference in the population proportions at the 5% alpha significance level? State the appropriate hypotheses for performing a significance test. Be sure to define the parameters of interest. Okay, so let's start with, let's define the parameters and so forth. So you're going to start with the hypothesis. So at least that's what I usually do. So the null is that, let's see, does it have names for these schools? School 1 to school 2. Okay, so we're going to say P1 minus P2 is equal to 0. The alternate, the ha, because of the way they phrased it, they said, does this of a difference in the population? So they didn't say one is bigger than another. So really, we just want them to not be equal. So you could either say P1 not equal to P2, or you could say P1 minus P2 is not equal to 0. Either way, you're using the not equal symbol there. So you want to also state that at the alpha level, so alpha equals 0.05. You also want to define the proportions. So P1 is the true, I'm not going to write it out, is the true proportion of students at school 1 that missed breakfast today. P2 is the true proportion of students at school 2 that missed breakfast today. Okay, so we define that step. That's kind of the what we call the state steps. Plan. Name the test. This is called a two-prop z-test. You could call it, if you wanted the formal name, I believe it's called a two-sample z-test for P1 minus P2. But that's the name of the calculator, and that's really helpful to know when we get to that step. Kind of double-check your answers here. So random, so you look for the word random. Let's see if we see it in here. Simple random sample. So twice it says simple random sample. So SRS for both groups. You have to check for both groups. That's a fine abbreviation to use. We know SRS, simple random sample. Okay, so large counts. Well, let's do less than 10%. So the first one was 80 students. So 80 is less than 10% of the students at school 1. And 150 is less than 10% of the students at school 2. So you kind of say that word. everything's the same so far. We haven't done much different. This is where things veer off a little bit. So this is a thing that we do. Here, let me see if it talks about this. Yes, we get that. Perfect. So let's stop for a second and kind of look at this. So begins by assuming the null is true. We call the common values of these values P. Okay, so we're going to pool these proportions together. It's called pooling or combining. The common, we're going to find the common proportion. Sometimes we call it that. So this is the formula we're going to need. And this is going to be needed for the large counts condition. That's why I stopped there, because you got to have this for the large counts for a 2-prop Z test. So it's really unique to this test right now, where you have to pool the proportions. So you basically just take, you kind of weirdly, you add up the numerators of both proportions, you add up the denominators, and then you divide those sums. So that's the notation. Notice the C there, it says P hat C. That's the common pooled proportion. So you combine both the number of successes and the number of individuals and get that pooled proportion, or the common proportion there. So when we get to large counts, you've got to use that in large counts. So instead of n times p or n times p hat, we've done both of those at 2 different times. Now it's n times, or the first n times, the pooled value. So both of them get, so you're only using pooled values for p in both calculations, right? So if we go back to the question here, so this would be, so n, so this would be 80, checking that condition, 80 times, well, let's find the pooled value here. So get our calculator out. So this will be as a fraction, so control divide. We're going to add up the successes in both. So 19 plus 26 over 80 plus 150. And I want a decimal, so I'm just going to put a decimal in there. So I get 0.19562. So you might want to show that work. So 0.1956. Okay, so that's going to be P hat C. It's going to be adding up the 80, or see, 26 plus 19, either order. I don't know if I did that the right order. And then the 150, the 80 and the 150, adding those up in either order, and you get this pooled value of 0.1956. So we're going to use that pooled value when we do 80 in the first one, 80 times 0.19. I'm just going to say, I think we can round that up to 0.196 there. So 0.196, that'd be okay. We're going to type that in our calculator, make sure that answer is greater than or equal to 10. We're going to do 80 times 1 minus that value. It's 3 digits, so it's a little hard to do in your head. You could do it, 0.804, I think, equals some value that's greater than or equal to 10. So that's successes. That's for the successes and fails for the first proportion, but you also have to do it for the other one. So it would be 150 times, also, so we don't use the individual p hats there, right? We're going to use the pooled value, so the 0.1956, 0.196, I guess, equals a number, hopefully greater than or equal to 10. You can use your calculator for that. And then 150 times 1 minus that, 0.196, is also hopefully greater than or equal to 10. And you check all those in your calculator, write them down. That's your condition. Okay, and so you're supposed to name the test. So you can say 2-prop Z interval. Usually with these kinds of things, you name it with a formula or in words. So if you forget to name it with the formula, with the words, hopefully you have the formulas, because that would count as naming the test, which is interesting. But that's almost always the way they phrase it in the grading rubrics. But always a good idea to write what it is. Interval, no, it's a test. Sorry, wasn't paying attention. 2 prop z test is what we're doing. We're not doing intervals. We did intervals just recently, but not right now. Okay, so the do section. So we are going to do, which is we have to find out what p hats are. So p hat 1, we still need these. So we still actually need to find p hat 1 and p hat 2, even though we found the pooled value already, which we'll use. We need to find these as well. So 19 out of 80 and 26 out of 150. So let's find those values. So 19 divided by 180 or 80 is 0.2375. I should say 0.24. And 26 divided by 150 is 0.17. Okay, so why do we need that? Because our next thing, so we found our p-values, that's great. We have to find z. So the formula for z is kind of intense here. So normally it's the sample minus the null. Well, what's the null in this case? If you look back, the null is 0, right? Either way you write it, the null is 0. So you're actually, weirdly, you're subtracting 0. So what's weird is the p hats, what you'll do is you'll do p hat 1, which is 0.24, minus p hat 2, which is 0.17. So that first term is kind of the subtracting the p hats there, right? You're just kind of doing p hat 1 minus p hat 2. That's what we stated at the start. That this is what we're going to do. So the denominator, you've got to figure out standard deviation. This is a monster here. So you're going to add, if you remember, it's like PQ over N, PQ over N. But again, just like for large counts, we have to use the pooled p hat here. So the common, so remember that common value, I think it was this guy, right? The p hat c, the common value is 0.1956. 0.1956 is p hat pooled or common p hat. So that's, we're going to use that in this standard deviation formula in the denominator. Well, z is the formula, but in the denominator is essentially standard deviation. So instead of np, it's going to be n for the first one. So n for the first one was, I believe, 80. So 80 times 0.1956. And then 150 times 0.1956. And then n was, what am I doing? I'm sorry. Thinking of a different formula there. Okay, the denominators are 80 and 150. Sorry about that. N1 and N2. The numerators are PQ. So it's to be 0.1956. I'm just going to say 196 times Q, which is 1 minus 0.196, or I think that's 0.804 is my guess there. And then again, PQ, so it'd be 0.196 times 0.804. Okay, and you type that guy into your calculator. It's a monster, right? And you'll get the z value at that point. So let's see what we get. So you go control divide. And we get 0.24 minus 0.17. I'm not too worried about the rounding I did there because I'm going to double check everything, calculate, probably adjust the numbers appropriately. Square root, I'm also showing my work, so pretty good with that. Control divide. So 0.196 times 0.804 over 80 plus control divide 0.196 times 0.804 or 1 minus, whoops, 1 minus 0.196 all over 150 We should get a decimal there. So our z value is 1.27. So we got the curve here. Here's 0. Here's 1. Here's 1, negative 1, I guess. Okay, 1.27 somewhere out here. So z equals 1.27. 1 standard deviation plus 0.27 standard deviation. So it's just a little bit of area out here. I mean, it's a little bit, probably a little more than what I drew there. It's a significant area. It doesn't look like a small area. Actually, if I drew this to scale, I didn't do my standard deviations the best. Because it's a two-sided test, make sure to think about the fact that it's actually on both sides. The same area is going to be on both sides there. So then you could do norm CDF, right? So you go menu 652. Lower bound was 1.27. That's a z value to infinity or a very big number, and just get it. So the area on the right there is that. To get also the area on the left, you multiply by 2. So I think the z value, I think the p value, I should say, should be 0.204. Whoops, 0.204. You can also say that as the probability that z is greater than 1.27 or z is less than negative 1.27, something like that if you wanted to. But it's 0.204 should be our p-value. It's a 2 there, really bad 2. Okay, so we've drawn the normal curve, we found everything. Let's check our calculator now and see if we get the same answers there, because it's really nice to do that. So hit the menu key. 6 is stat, 7 is stat test. Let me scroll down to 2 prop z test. That's the one we want. Really easy tool to use here. So it's, I think it was 19. The first one, you have to go in the same order. You want to make sure that P1 is first there. So 19 out of 80, and then 26 out of 150. And it defaults to the not equal to, which is definitely what I want here. So I'm going to say, okay. It gives me z is 1.16, which is a little different than 1.27, just a rounding error there. The p-values, 0.242. I got 0.204, so 20.4% compared to 24%. Which one's more accurate? The calculator is definitely more accurate there, so 24%. But either way, I'm making the same decision. It's not crucial in that sense. P1, and P2, let's see if we had those correct. 0.24, 0.2375, 0.17. Yeah, that's right. And then, oh, look at this. So do you see on the calculator what that P hat is? That's our P hat common, our common P that we get from pooling. So if we look at that, that was 0.1956. That's exactly what it is, 0.1956. Excellent. So it gives you all those values. Again, so if you're just writing, if you're not showing the work on the do section, make sure to name the test, 2 prop z test. Make sure to put the z value, the p value, the p hats, and the common p. I would put all those values on there. It wouldn't hurt to put N1 and N2. I mean, just copy all those values. I'm not sure N1 and N2 would be crucial there. We definitely might look for that p hat pooled value to see if you did that or not. That could be part of a question there. So just put those values on your thing. Put the z value, obviously, 1.16 and the p value. Those are probably the most important ones to have, because those you're going to make your decision with that p value of 24%. Oh my. Okay. So then the conditions. So we've done norm CDF. At that point, you're really ready to conclude, make your conclusion. So you always want to start with, because our p-value was p-value of 0.24 or something like that. I think it was around 24%. Is less than, no, not less than, is greater than our alpha level of 0.05, we fail to reject. we don't. So we do not reject. We don't have evidence. To say that the difference, the true difference in proportion. So that's the difference with what we've been doing, the true difference, that the true difference in proportions is not equal to whatever our null was, which was that are not equal. That true difference in proportions are not equal, right? That's what we think. The true difference, and let's talk about what they are. The true difference in the students who ate breakfast today at both of the different schools, that they're not equal. So we don't have enough evidence to say they're not equal. They might be equal, we don't know. But we know we don't have enough evidence to say they are. So this is what they said. Oops, sorry, let me get this out of there. I don't know if you can see that or not. Oh, there we go. Okay. So on this one, whoops. I don't want to put that on there. Wow. It's really frustrating. Sorry. There we go. Now we're talking. Okay, so there's the large counts condition. Standardized test, that's the formula for the z-score. It's called the standardized test statistic. You may be tempted to put P1 and P2 in there, very possible, but we can't. We have to pool those. So that's actually the formula with proper after you've pooled. So that's the one we use for 2-prop z-tests. And so they didn't go through all the steps there, but I think we have those done, and we'll save the next example for the next class. Okay, that's our lesson for today.